In Calc 1, we saw this nice theorem about how the derivative of an inverse function relates to the original function. And it said that if f of x is invertible, then the derivative of its inverse is just 1 over the derivative of that function evaluated at the inverse. We used this to find the derivative of natural log, because we had already found the derivative of e to the x, and so natural log is its inverse. So we used that idea there. I want to use it today to derive the derivatives of the inverse trig functions, at least sine inverse, cosine inverse, and tan inverse. All three of those are invertible, at least on those restricted domains. Remember, over their whole domain, they're not invertible, but where they are, that's what we're talking about. So first, we'll start with the function f of x is sine x. Okay, so this tells us that sine inverse's derivative should be 1 over the derivative of f. So the derivative of sine is cosine, evaluated at sine inverse. All right. And technically, we could be done right there, except for this does simplify. Whenever you're composing inverse trig functions inside of trig functions, that can simplify. One way of doing that would be to take advantage of identities. Cosine, if I could write cosine in terms of sine, then I could cancel with the sine inverse. Well, we could use our Pythagorean identities. So cosine would be, remember, sine squared plus cosine squared is 1. So cosine would be the square root, if we solve that for cosine, square root of 1 minus sine squared of sine inverse of x. Just using the fact that cosine squared is 1 minus sine squared. And then now that these are a function and its inverse composed, that's just going to reduce down to square root of 1 minus x squared. Now, I cheated a little bit here. When I did this square root, technically we should have plus or minus, right? From the Pythagorean identity, when I solved it for cosine, it should be plus or minus that square root. So why did I just ignore the minus? Well, I need to think about where we are actually at on the sine function and what that means about the sine inverse. So if you look at the sine inverse function that we just reviewed, the slope is never negative. So this thing will always be positive. So we know that it's not the negative part, it's just the positive part. So I'm able to drop that from my knowledge of what the graph looks like and realizing that the derivative represents slope. So we don't need the plus minus on that. Likewise, let's look at tangent. So the derivative of tan inverse according to our theorem here is it should be 1 over the derivative of tangent, which is secant squared, evaluated at that inverse. And again, I'd like to rewrite secant in terms of tangent so I can cancel the off there to simplify that. So again, the Pythagorean identity comes in handy. Tangent squared plus 1 is secant squared. So this is tangent squared of tan inverse plus 1. And so just 1 over x squared plus 1. That time there was no square root, so I didn't have to worry about pluses and minuses. The last one here we will do will be secant. So if we're looking at secant x, according to our theorem, the derivative of secant inverse should be 1 over the derivative of secant evaluated at secant inverse. Well, its derivative is secant tangent. So it's secant inverse times tangent secant inverse. Secant inverse cancels, leaving an x. And then I need to do the same thing I did before. I want these guys to cancel, so I need to use a trig identity that's going to require square rooting. I'm going to use the same Pythagorean identity. Tangent squared plus 1 is secant squared. So tangent is plus or minus the square root of secant squared minus 1. So secant squared of secant inverse minus 1. Now, I didn't write the plus minus again, but if we look at secant inverse, its slope is always positive. So what does that mean about the plus minus? Well, I'd like this to always come out positive. The square root's always going to come out positive. But the plus minus, really what I need to do for that is really take the absolute value of x, because for negative x's, I still want this to come out positive. For positive x's, I want it to come out positive because the slope of secant inverse is always, on those two pieces, it's always positive. So lastly, if I can squeeze it in here, be 1 over, nope, I'll start it up back here. 1 over the absolute value of x, square root x squared minus 1. So the absolute value is because I know the slope has to be positive, and that's really how I'm dealing with that plus minus from taking that plus minus square root. And so because of our domain restrictions, we know only certain things can happen with the slope, thankfully. So derivative of sine inverse, 1 over square root of 1 minus x squared. Derivative of tan inverse, 1 over x squared plus 1. And derivative of secant inverse, 1 over absolute value of x, square root of x squared minus 1.